Let's take a look at, if we have a circuit with a high quality factor, how we can use approximations to simplify our circuit analysis. If you recall the parallel RLC circuit and the pole zero constellation associated with the input admittance of this circuit in terms of as a function of S, where we had our zeros at negative alpha plus or minus j omega d here, and we had a pole here at the origin. Well, this alpha, that's 1 over 2 RC. That's also equal to 1 over 2 times omega naught over Q naught. That's half the bandwidth, right? So this here we can relate to this negative alpha is at 1/2 the bandwidth. And our omega d, that was our omega naught squared minus alpha squared. So what we want to look at is if we have high Q approximations. High Q, we're saying, is when our quality factor at resonance is greater than 5. We can say greater than or equal to 5. This says greater than 5 there. So again, if we look at that, our alpha, if we plug in here for our alpha, our 1/2 bandwidth, then the zeros of our admittance function are at 1/2 the bandwidth down here, plus or minus j omega d. So if we zoom in on this portion of our pole zero constellation, where we have our S1 up here and our S2 down in there, where we have a negative radian frequency, this plus or minus our omega 1 and omega 2 here, that's where our half bandwidth is. This is where our zero, our zero is, but these are where our bandwidths are. That's where our omega 1 is approximately equal to our j omega naught minus 1/2 the bandwidth. So let's show that. So if we look at our omega d, we can substitute in for our quality factor. That's 1 minus our alpha squared, 1 over 2 times the quality factor squared. If we're at high Q approximations, this number, for example, if it's 5, that's 1 over 10 squared, so that's 1 over 100. So we're really approximately equal to 1/2 the bandwidth plus or minus just our j omega naught, right? So that's where this is our j omega naught. It's really 1/2 the bandwidth plus or minus j omega naught there. So again, our omega 1 and omega 2, we solved for those. That was this radical term here. If we're at high Q approximations, this is going to be approximately equal to 0 relatively. So we get our 1 minus plus 1 over 2 Q naught. And our 1 over 2 Q naught, that's our bandwidth. So our omega 1 and omega 2 are omega naught minus plus 1/2 the bandwidth, just saying that omega 1 is on the negative side. It's a lower frequency. So they're symmetric around it. High Q approximations are half power bandwidth frequencies are symmetric around omega naught. And the sum of the two is approximately equal to 2 times omega naught. And again, for high Q approximations, you can substitute in a 5 for Q or higher to get that. So again, and also each of our half power frequencies are located about a half bandwidth from the resonant frequency. So that little half bandwidth from the resonant frequency. And again, we can look at this on our S-plane. So if further approximating for high Q, if we visualize a test point above omega naught, so here's our omega naught, here's our test point here above omega naught, and we want to determine our admittance function at this frequency, we can construct a vector from this location to each of the critical frequencies. So we have a critical frequency at our S2 way down here. It's far enough away and close enough to the j omega axis that we can say that's approximately just equal to 2 j omega naught. And from the origin, well, we're going to say that's approximately just equal to j omega naught, because we're saying our omega d is approximately equal to omega naught there. Or excuse me, not our omega d, but our omega 1 and omega 2. So what we really need to just evaluate is this vector here. So our admittance function is approximately equal to 2c times that our operating frequency S minus this S1 here. So if we look at just that S minus S1, our S is j omega, and our S1, that's that half bandwidth plus j omega d. We're just looking at the positive radian frequencies. So it's or equal to our half bandwidth plus j times omega minus omega d. And then that's approximately to 1/2 bandwidth j omega minus omega naught. So if we look at using that, evaluating our upward zero vector in that way, we can then look at our y as a function of s as 2c times, we're plugging in for our s minus s1, our 1/2 bandwidth times 1 plus our j omega minus omega naught over that half bandwidth. Just using some algebra here to pull out the 1/2 bandwidth in both of these terms, and when we substitute in for our 1/2 bandwidth, for our 1 over 2 RC, right? That's our alpha. Then we can cancel the 2's, we can cancel the c's. We end up with just our 1 over r times this term here, and that's approximately equal to our 1 over r, right? This becomes just 1 over r. This is 1 plus, what is this number here? Our 1 plus omega minus omega naught divided by the half bandwidth. That's j times, that's the number of half bandwidths off resonance, right? So again, omega is that operating frequency, and we're subtracting out our resonant frequency and dividing it by the half bandwidth. So that's the number of half bandwidths we are off resonance. So we can determine at high Q situations our admittance just in terms of the resistance and the number of half bandwidths off resonance. So that's the approximation that we can use for high Q circuits. Remembering, what we're referring to as N, that's omega, that's our operating frequency, minus the resonant frequency of the circuit divided by the half bandwidth of the circuit. And these are all calculated by omega naught, and the bandwidth are calculated by the characteristics of the circuit. So again, so this asks us a question at half power bandwidth, omega 1, the N is what? N is 1. That's 1/2 power bandwidth off resonance. So our admittance function there is, when we plug in the 1, we get the square root of 2 over r, and our angle is just the tan inverse of n. N is 1, so the tan inverse of 1, that's 45 degrees, right? So that's for omega 1, right? So omega 1 is our lower half power bandwidth, so that's approximately 1 over r times the square root of 1 plus 1 squared, or square root of 2 over r. If we're at omega 1, tan inverse of 1, that's equal to 45 degrees. If we're at omega 2, right? So if we have our omega naught, omega 1, omega 2, then our omega minus omega naught. So actually this is for omega 2. At omega 1, we're actually going to be at tan inverse of -1, so that's going to give us our -45 degrees. Magnitude will be the same. Angle, we're going to get a -45 degrees for the lower half bandwidth frequency. So that's our high Q approximations. High Q approximations are appropriate if Q is greater than or equal to 5. Also, the circuit has to be operating within 10% of resonance. So that operating frequency omega, that's got to be between 0.9 omega naught and 1.1 omega naught. In the next video, we'll look at an example.